Alrighty. Well, it is time, and I got the recorder started. Is the Are you guys still smelling the smoke? Is it bothering you, or is it kind of okay? Yeah, that's kind of what it smells like, just a little bit. All right, cool. All right, so a few things. Exam two is coming up. It's going to be next Thursday, so you might want to write it down in your calendar. That is correct. It will be on the 10th of April, but we'll talk about the exam from last semester on this Thursday. So that's kind of the plan. I always give a week, kind of space out, week by a week between when we have a practice from the previous semester and when we're gonna have our own exam for that semester. Yes, that is correct. Yep. So you can see, I mean, not today, but on Thursday, we'll be talking about the exam from last semester. I do encourage all of you to kind of work on the exam that is included in the announcement. If not for anything else, just to check your knowledge and see how, where you are in terms of, answering those questions. It might also inspire you to kind of work on your notes and also your study guide that you can bring to the test. Okay, so you might want to kind of use this opportunity to find out, okay, what else do I need to bring to the test? Okay, so in terms of the scope, this is not a bad representation of what is going to be included in exam two, but in terms of the actual format of the question, mm, I don't know yet. I still have not made up for the questions for this semester. So, that part is certainly a variable. So are we good so far with all that? Yes. So in the exam, it's going to be on paper. So you are not going to have access to the assembler as a tool, but as a language, you will be tested on whether you understand the instructions or not. Okay. But remember, you are allowed to bring in any number or any amount of printed material or handwritten material. You guys can even work together, okay, as a group to come up with the material that you think, okay, we think that this is going to be useful in the exam. It's okay as long as there is no collaboration during the assessment. It's okay. You guys can study together, not a problem. But when it comes to assessment, it has to be individual, unless you guys have plans to kind of bound to each other throughout your entire career. It's like when I get into a job, so is this entire group. But if anyone gets fired in this group, we are all going to get fired. So if that is the agreement, I can see the value of group assessment, but otherwise, I do not see any value in group assessment, especially for a class like this. All right. So do we have any questions about exam two? The scope is up to and including, I would say, the material that we talked about last week. Okay, so you're starting to write simple programs using TTP ASM. Okay, but what we'll be starting today, which is the concept of a stack, how to call and how to return from functions, that is not on the scope. Okay, so are we clear on the scope of the exam? Okay, so take a look at the exam from last semester if you have not had access to stuff like this before, so that we can use Thursday to talk about the answers to the exam from last semester. All right, so with that said, there's another piece of announcement, and I'm not sure how you guys want to do it. So for today, I can go one of two routes, or we can prioritize this in one of two ways. We can start to talk about calling and returning, like the first thing, and then we can go back and talk about the decompiling of a program to figure out the control structure of a program. Or we can reverse the two, and we can start with decompiling a program and then continue to talk about calling and returning using the stack and stuff like that. So do we have any preferences in terms of the order? Yes, please. calling and returning? Well, the program that I have in mind for decompiling does not involve calling and returning. It only involves your control structures like while loops, conditional statements, and so on. So these two are somewhat orthogonal, I would say. Any thoughts? Any preferences? Yes, please. Um, I would say decompiling is more relevant to the lab. Okay, I guess that would. Okay, that sounds good. So once again, the key is knowing what question to ask. Okay, so I have talked about this multiple times, because in the age of AI, it is knowing what question to ask that makes humans valuable. It is the AI can outknow you any day. Okay, it can possibly outthink you a little bit depending on the kind of problem, but it cannot out ask you. Okay, because you are the person who has to prompt the questions because you can only you can determine what is important to you, such as, oh, do we know enough about the lab? Do we want to work on something that is important to the lab? Yes, please. Say again. No, every day is a April Fool's Day, and the joke is on me. Yes. So there's a song, I think it's from the Bee Gees, and the Pet Shop Boys sung it again, but what is the name? Um, the joke is on me, Bee Gees. Okay. I started the joke. Yeah, so this is one of my favorite music, and I mean, it's not important in this class here, but since what you said, I just go like, okay, well, I guess I start a joke every day, multiple times. All right, so what we'll do today is to first talk about the decompiling of a program, and then if we have time, we'll use the remaining of the time to talk about calling and returning. Okay, so let's go ahead and get started. And I just fixed a problem that I saw earlier today, which was kind of annoying, but I got it fixed already. Basically my editor would not use the color scheme correctly, so but I got it fixed already. So I'm going to share with you a piece of, oops, wrong folder. You guys cannot see anything yet because I'm doing this on a command line that you cannot see just yet. Okay, so here we go. All right, so this is the assembly code of a particular program. I don't care about whether the variables are global or local. We can for now consider the registers as our variable. You can see there are six. I mean, there are four of them because registers A to D are all utilized here. But what I do want to know is how do we decompile this code back into C code? Okay. Now, when I say C code, I don't care that much about whether you remember to put a semicolon after each statement or each assignment or not. That is not the goal. Okay. The goal is, can we figure out the control structure of this code, which are there are only three that we have talked about. We have conditional statements, otherwise known as if then else statements. We have pre-checking loops, which most people call while loops, and we also have post-checking loops, which most people call do while loops. Okay, but those are the only three control structures that we have. So we look at this code and ask, how do we reverse this code and figure out what it looks like in C code? Yes, please. That is correct. So unless I specifically, introduce unnecessary jumps and unnecessary labels to confuse people, this one does not fall into that category. That means every label and every branch is important. Okay, so we start the analysis of those. So now we look at this and go like, there's a label on line 6. There's a label definition. In other words, we put label L1 on line 6. It must be for a good reason because I already told you that I did not intend to trick you, even though today's is April 1st. Okay, so that means, we might want to find out why that label is important. How do we do that? We see label L1 being defined on line 6. So how do we know the significance of label L1? Please go ahead. References, yes. So you are correct. So we need to look at references of L1, and there's only one on line 15. So line 15 is the only line that references label L1. So let me just kind of highlight L1. Let me see. Oh, okay, my cursor is on the wrong page. There we go. So this is why I kind of like VI, but most editors do this anyway. Is when I search for a pattern, it highlights all occurrences of that pattern within the view of a file. So we can now say that, line 6 is L1, and then line 15 is a JMPI to L1. So right away, what can we decide? There are three control structures: conditional statements, pre-checking loops, and post-checking loops. Which one can we rule out right away? Let's just say that we want to rule out one of the three. Which one can we rule out right away? Yes. That is correct. So the conditional statement is the one that we can rule out right away because with a reference or JMPI to L1, after the definition of L1, we have some kind of a loop because control or execution is going to go from line 15 back to line 7 if the JMPI instruction is to execute. Yes, please. Go ahead. Well, we didn't talk about for loops. So now we only have two choices left. Okay, we have ruled out one of the three possible control structures. We have just ruled out conditional statements. So the other two, one is a while loop, which is a pre-checking loop. We check the condition, and if the condition is false, then we get out of the loop. The second one is a post-checking loop, where we perform the operation first, and then we kind of decide whether we need another iteration or not. Yes. Okay. Well, let's look at the label and the references to label again. Okay, so with a post checking loop, how do we get out of a loop? After the operation, so that means either the last jump instruction is a conditional branch instruction, so that the branch back to L1 is conditional, or there is some other kind of mechanism to branch out of the loop. In this case, which label do you think marks the exit of the loop? In other words, if we get to this label, it means we're out of the loop. Yes, please. L2, that is correct. Okay, so L2 is marking, quote unquote, oh, if we get here, we're out of the loop because JMP L1 is to go back to the beginning of the loop. Is that okay? Does everybody understand the analysis of as to the purposes of the labels? Okay, very good. So once we have identified L2 is marking, oh, if we get here, we're out of the loop, what do you think is the next thing that we should do? Okay, you already mentioned earlier the references of that label. In other words, where did we use label L2? Line 16 is the definition of L2. Line 8 is the utilization or the reference to L2. Okay, so now our attention is now back to line 8 because it contains a reference to the label L2. So we look at L2 or how it is used. What is the instruction on line 8 that makes use of label L2? Go ahead. That is correct. Go ahead. Okay. Yep, go ahead. No, something was burning, not is. Something was. Okay, technically we are all burning. It's called metabolism. It's a oxidation of carbohydrate. So we are all burning. But since you're asking about the smell that we are smelling, that is from earlier. There were what, four fire trucks in the parking lot earlier. Somebody started a fire in a trash can in the bathroom right next to here, and then the smoke permeated to all the rooms. So unfortunately, this room got a little bit of the smoke, but there was an attempt to ventilate the room already. So is that too much for you, or it's just you're just concerned that whether I'm on fire or not. Okay. Yeah. Okay. I don't think. Okay. So to answer that question, we're all gonna die. Probably not today and in this room. Yes. Yes. That's my answer to everything. Is like, yeah, that can happen. The question is it gonna happen today in this room? So the answer is probably not. Now, do I rule out the possibility of that happening because of some electrical fire? No, I cannot promise anything. I can just say that it is very improbable. That is true. It depends on where it starts. If it starts at all the exits first, well, what if all the exit signs you'll start the fire first? Like the exit signs literally just light up because they're on fire. Okay, I have to think of all these possibilities. Okay, that's kind of how my brain works. Okay, it's like how can I come up with a situation where something unlikely is going to happen? So I do apologize for distracting you guys from the main discussion here. Okay, it is fun, but it's not relevant to the class. All right, so we look at line 8. Okay, it's a JCI instruction. It is a conditional branch to L2. So can we now answer the question again of whether this is a pre-checking loop or a post-checking loop? Is the condition checked at the entry point of the loop, or is it checked at the exit point or at the bottom of the loop? Entry point, that is correct. In fact, what do you think of line 7 and line 8? Obviously, JZI is useless unless we have a mechanism to set the flag, the Z flag, right? So in this case, the AND CC instruction is used to affect some of the flags, of which only the Z flag is used on line 8 to perform a conditional branch. So if we are to comment these two lines, okay, what do you think is going to lead to label L2? Okay, it's a while loop, but what about register C that is going to cause us to go to L2? C has to be 0, okay? So that means if C equals to 0, we are going to L2, but we already know this is a loop. So that means if I were to rephrase this as a while loop, what is the condition to stay in the loop? Yep, while C does not equal to 0. No, well, I mean, that's technically okay. You are correct that in some cases we can say that when C is greater than 0, but in this case, we until you get to line 11, you don't know whether we're dealing with signed numbers or unsigned numbers. With signed numbers, when C is not 0, it does not automatically mean that C is greater than 0 because it can be less than 0 in the case of a signed interpretation. So before we get to line 11, we can't really come to that conclusion that C is unsigned because we don't have any clue as to whether it is signed or not. So the only conclusion is while C does not equal to 0 because we don't know yet what is the type of register C. Good? Okay. So now we have figured out certain things. Okay. So we have now figured out this is a loop, this is the beginning, and this technically marks the end of the loop. Yep. Go ahead. That is correct. Okay, so we have accounted for uh, two labels so far because L1, the job of L1 is, oh, we need a way to go back to the beginning so that we can do something again. Okay, so that's the job of L1. L2 is related to L1 because if you can have a mechanism to go back to the beginning of a loop, and it is the branch itself is unconditional on line 15, then it becomes an infinite loop unless you provide a way to get out of the loop. So the job of L2 is for us to get out of the loop. So L1 and L2 are related because one is for us to go into a loop, and then the other one is for us to get out of the loop. So now we have another label definition, which is on line 14. It is L3. In this case, the only reference of L3, let me highlight L3 so that we can see all the references of L3. So the only reference to L3 is the branch instruction on line 11, which is a JCI. It is a conditional branch. So but it's not a branch backward. Okay, so when you don't see a branch backward, either it is a conditional statement or it is a way for us to exit a loop, one or the other. Okay, but in this case, we don't see any code to go back to a point right before the reference of L3. Okay, because we have already accounted for L1 and L2, so we don't have any additional loop. This is a conditional statement. Okay, it tells you that we have a conditional statement. Yes. On line 13, uh-huh. So the point of the C code is not important, even though in this case it is actually a fairly important code. But in this case, our concern is, how do we convert from assembly code back to C code? Nope, it won't do it forever. Okay, this is actually a way to perform division, um, and it is also a very quick way to draw a line on a screen when they are pixelized. So it does not involve actual division or mod or anything like that, and yet it can draw a line once you specify, excuse me, once you specify the slope. So it's a very interesting mechanism for drawing straight lines that is on the slope on a screen. Yep. A and yes, some of the yep, yep, and C also changes because otherwise we'll be stuck in an infinite loop. All right, so this one is not in a control structure, but when we look at this instruction here, it is saying if blah blah do something, and L3 is for a way for us to skip the other two lines here. So we are looking at the closing of the conditional statement. Let me use the correct indentation so that we can use indentation to imply the nesting of the control structures. So now the question is, what should I put inside the parentheses on line 10? In other words, under what condition do I perform the decremency and the sub dB? It is not. If it is less than, we are branching. It is the other way. That is correct. So if B is greater than or equal to B, we we execute the body of the conditional statement, because if not, it is less than, and we go to L3, which means there's no way we will execute line 12 or 13. So, huh? Oh, okay, I type two B's. If D is greater than or equal to B. But this one, this compare, the JCI also tell us about the type of the two registers, or how we should interpret those registers, because it is a JCI instead of a JLI, which means, we now know that D, B are both unsigned. Now, does that automatically mean that A is unsigned? The answer is yes. But does it also automatically imply C is unsigned? The answer is no, because there's no direct interaction between register DB with register C. Register D does interact with register A, which implies they are of the same type. Is that okay? So this is like playing detective, right? You see the clues and then you just ask the question, okay, why is this here? What does it do? And so on. So I think this is really important, in the sense that um, you, you, the ability to solve a puzzle, to ask the question, to go like, okay, what is going on here? Okay, why is this label here? Those are important skill sets in the workplace. So now that we have all this done, the rest is pretty easy. Okay, because this instruction here is simply saying, oh, okay, we just need to add D add register A to register D, and the simplest way to put it is exactly that. Okay. So has everybody encountered this plus equal to operator in C++ in your CISP 360 class? Okay, excellent. Okay, and what is the name of this type of operator? Okay, a single equal is assignment. So this one is blah blah assignment. Okay, what is it? It's called a compound assignment operator. Okay, sorry? It is plus equal to, so we are adding A to register D. It is the same thing as D equals D plus A. Yep, it's a compound assignment operator. Not that the name is super useful, but it is kind of important. It is important to know what it does. That's for sure. So this one is easy, okay? Minus minus C or C minus minus or C minus equal 1 or C equals C minus 1. They're all the same, okay? It makes no difference whatsoever which version you use. I just use minus minus C in this case. And now this one is D minus equal to B because we are subtracting B from D. And that's it. That's the original C code. The comments. Oh, wait, I missed a few things at the beginning. So the few things that I missed at the beginning, they're not really that important because they're kind of obvious. A gets a value of 3, B gets a value of 7, and then C gets a value of 4, and then finally D gets a value of 0. There we go. All right. So this is important for your lab today because in the lab there are two higher value questions where I give you a chunk of code and I ask you what happens to a certain register at the end or when it halts. So there are several ways to answer those kinds of questions. Number one, the best way that I think is the intention of the lab is to perform an analysis like this, and then you use the C code to try to figure out, how what it is going to do to the registers. Okay, so that would be the best way if you can. Okay, the second way is to go like, okay, I can run this through Logisim and then just check the value of a register, yeah, you can do it that way too. Okay, not really the best way to do it, but if you run out of time and you go like, I really want those 4 points, that's a way to do it too. Okay. Um, the third way is to make use of River Spider. If you already have it set up, you can just kind of run it. The nice thing about running this program using River Spider is it gives you a clue. Like you can definitely tell in the loop something is happening over and over again in the trace. Okay, if something is conditional, you can see it skipping certain things. Okay, so that's actually kind of a nice thing of using River Spider as an aid. Okay, as a way to help you understand what the code is actually doing because it leaves you an entire trace of how the code executes. Yes. There are no existing tools that I know of that can do that. That's that's why we are doing it by hand. Yeah, so those are the three ways of doing it, and there's a fourth way, which I would call the infinite monkey approach, because you know that the answer is going to be an integer, and you're just going to blindly poking and see which integer is going to work out. So that would be the least useful way in whatever way you look at it um, to get the lab done. Yes, it is in the if statement because the skip is going from line 11 directly to line 14. So everything in between, after the conditional branch and before the label that it branches to, they are all a part of the conditional statement. Now, there's a technicality of whether it is a single statement or two different statements. So let me just kind of confuse the class a little bit here. You can make it a single statement by changing this, semicolon to a comma. As it turns out, comma is actually an operator in C++. So comma allows you to string multiple sub-expressions into a larger sub-expression. The job of a semicolon in C++ is to turn an expression into a statement. Okay, so in this case, we actually get to choose. Okay, you can use a comma instead of a semicolon because you can combine the two expressions into one single expression, into a comma separated expression, and then terminate the entire thing using a single semicolon. Or if you use a block statement, which are implied by the braces, then you can look at this as, oh, we can also consider this as two separate statements. Each one is based on an expression. So that's a different way of looking at things. I mean, it's more or less a compiler thing, but as far as I'm concerned, as long as you choose one of the two ways, it's good. All right, so that is it. Okay, but this also kind of give you an idea of where you need to be in order to continue with the content. I would say that the class is continuing at an even pace. Okay, so I have not really taught the class any faster than before, but the material is compounding for sure. Okay, in other words, there's a linear dependency on the material more so than ever at this point. So that means being familiar with the instructions or the mnemonics is actually super important at this point. Okay, knowing the instructions in the opcode table is really important. Okay, so right now I just want to emphasize that so that people understand the importance, and that gives people a chance to at least try to catch up before the next exam. All right, so this is it. Okay, this is decompiling, which is actually a valuable skill set because this is how people can reverse engineer code where the program is already compiled. Okay, so now we are moving on to the actual topic. Okay, because now we are moving on to the discussion of calling and returning. And there's a module that is already written on that topic. So let's go to that particular module. Okay, and we are going down to assembly language programming. This is the lab for today, and this is for probably on Thursday, depending on how much we can go over in calling and returning from subroutines. So this is the topic for today. All right, so I'm going to show you a piece of code like this. And this is the kind of code that I'm showing my CISP 300 class right now at the same point. Okay, we are trying to understand, what is function calling and what is function returning. So the magical part about function calling is how does the function know, the called function, how does it know where to return to? I mean, going from main to F function F is not a problem. Okay, a JMPI to a label F can do that. Okay, so going from the invocation to the function being called is not a problem. Easy peasy. It is when F is done, how does it know the first time it has to go back to the second call of F, and then after the second call, it knows it has to return to the return zero line. How does it know that? So that becomes the puzzle. So in order to answer the question, we're gonna have to we're gonna have to talk about something that does not seem to relate to function calling. It is the concept of a stack, okay, which is um, uh, which is a way of storing something and retrieving something. Okay, so at the abstract level, the concept of a stack is called LIFO, LIFO, which stands for last in, first out. Okay, so we encounter a lot of last in, first out situations in real life, sometimes intentional, most of the time unintentional. Okay, so let's think about mm, a U-Haul truck. Okay, you're trying to help someone to move to a different state. So somebody rented a pretty long, huge, big U-Haul truck, and the last item that you push onto the truck before you slam the tailgate is going to be the first thing to fall out of the truck when you get to the destination. And therefore, it is a last in, first out mechanism. Does that make sense? Okay. There are many other mechanisms where it is last in, first out, even though, well, it really should not be last in, first out. I'll give you an example. It's the refrigerator. So unless you're very disciplined, okay, and you say, I'm gonna finish whatever is in the refrigerator, like all the way to the back before I buy new stuff, then chances are you got some stuff that is colorful, kind of growing, some organism that you don't want to know about at the back of the refrigerator. Because as much as we want the refrigerator to be used in a FIFO, which is first in, first out way, the organization of the appliance is actually more of a first, last in, first out way because it only has one door. It's the same door that you put stuff in and the same door that you take stuff out. So the last jug of milk that you put into the refrigerator, guess what? It's the first jug of milk that you're going to use that you're going to pull out of the refrigerator. So that means all the other stuff in the back of the refrigerator, if they used to be milk, they would turn into cheese. That is correct. Okay, unintentional cheese. Yes. So so that's last in first out. Do we have any questions about the concept of last in first out? We're good with that one? Okay, excellent. So understanding the whole concept of last in, first out, now we define those two terms, okay? So the word push is basically putting stuff into something, and the word pop is to mean that we are removing something. Is that okay? Push means we are putting something into the U-Haul truck, putting it into the refrigerator, and then pop means, oh, just grab whatever is the last thing that, or the first thing that is accessible out of the U-Haul truck or the refrigerator. Are we understanding those two terms? Push and put, push and pop. Okay. So if we are to understand this as a sequence, so that means the operation of push 24 is going to, guess what? Store 24 onto the stack. The use of square bracket here does not mean that we are using an array. I just need some kind of mechanism so that I can mark the beginning and the end of the stack. So I just use your square brackets in this way. So now we push 61. Okay, so the next line says to push 61, which means we now also want to store 61. So the front of the stack or the top of the stack is in this representation, the leftmost item in the square brackets. Let me say that one more time. The top of the stack, which is representing, if I need to grab something, I'm going to grab that thing. That is the leftmost item of whatever is in the brackets. So if we push one more time, and this time to push the value of 11, then 11 becomes the top of the stack. But 61 is still right after that, and then 24, which is the first item that we pushed, is right after that. So imagine that you are loading up a U-Haul truck. Okay, the 24 is the first thing that you load in the truck, which is usually going onto the granny nuke, I guess. U-Haul has a term for that little overhang area, that is on top of uh, the truck itself. And then 61 is the next thing that you push, the next thing that you store in the U-Haul truck. And then the 11 is the bicycle that you try to push onto the truck right before you slam the tailgate. It's the first thing that fall out of the truck. Okay. So are we good with those concepts? Okay. So when we pop, then the first item that we pop, the first thing that we remove or retrieve is going to be 11 because it is the one item that is sitting right next to the tailgate just waiting to fall out of the truck. If we pop again, it'll be the thing that you're storing second, which is our 61. And if we push again the 5, then the 24 is not retrieved yet. So it is still on the stack. And then we just push a 5, which means now 5 is the most recent item that we push on the stack. And then we can push another thing, which is 78, sorry, on the stack. So at this point, if we are to perform a pop, it will retrieve the value of 78, and we push 100 again, then 100 is going to be here, and we pop again, it will be 100 being popped. So are we understanding the sequences of pushing and popping, looking at a stack no more than just an abstract way of, oh, we can stash something here, but it has a very specific order of the last item that you push in is the first item that you pop out. Yes, please. Mhm. So there are instructions following this, and starting with a C implementation. and then later on to convert into actual assembly instruction. So those questions will be answered. Yes, yes. I specifically follow the same order as a push and a pop as an array method in JavaScript. But since this class is not about JavaScript, I did not make any references to JavaScript array push and pop. There we go. All right. So the way we implement this in C code, okay, because C is as close as you can get now with Rust, Rust 2 to assembly code. So the way we implement this is we simply define the stack as an array of unsigned 8-bit integer because inside text processor, everything is only organized as bytes. It is a byte, is an 8-bit processor. So the first line, which is the line where the cursor is simply declaring an array called stack. It has 32 locations, and that's all. So the next line is defining what we call a stack pointer. SP stands for stack pointer. So the stack pointer points to obviously to something, right? So there are two standards. Um, in my class, the stack pointer always points to the last thing that you push on the stack. Let me say that one more time because this is actually kind of important. In this class, the stack pointer points to the last item that you push on the stack, which is also going to be the first item that you're going to retrieve in a pop. Because the alternative definition of a stack pointer is the next available location to push an item, which is not how we use the stack pointer in this class. Yep. There's no head or tail because it's a stack. It is the top of the stack. The stack pointer always points to the top of the stack. So that means to represent an empty stack, we're gonna need some trick, okay? Because it always points to the last item that was pushed on the stack. So what if the stack is empty? I have not pushed anything on the stack. Where should the stack pointer point to in that case? So we'll get to answer that question in just a little bit. So the stack pointer is also used in a reverse way. So before answering the question of how we initialize, this is how we push an item on the stack. So we decrement the stack pointer, and then we store x to where the stack pointer points to. So these two lines represent how the stack pointer is utilized in order to quote unquote push x on the stack. Is that okay? So we're good. Yep, go ahead. Because the stack grows downward in terms of memory space. The stack pointer, if when the stack is empty, the stack pointer is actually pointing one location past the end of the array. And as we push items on the stack, it decrements first to quote unquote allocate for the space that for you to store a new item, and then it overwrites that location with the value that you want to store. Nope, it has to do with, so this is a standard that is true across almost all architectures. So when you look at how the stack is utilized by the x86 architecture or the ARM architecture or the PowerPC architecture, they're all very different in many other ways, but the way they utilize the stack is still consistent. Okay, you start at a high location when the stack is empty or very close to empty. And then as you push items on the stack, it moves down. The stack pointer moves down. And there are good reasons for that too. So we'll look into those reasons, when we get to um, parameters and local variables. Yes, up and down is just a matter of perspective. But this is the order of the operation. We reserve some space on the stack by decrementing the stack pointer because remember the stack pointer points to the last item that was pushed on the stack. So I have to move it one way or the other in order to quote unquote make room for the space for the new item that I need to store. So in this case, the stack pointer moves down as we push more items onto the stack. You just kind of have to accept it as is right now. The reasoning of why we do something like this is explained later. Yep. Yeah. Oh, yeah. Uh, hmm? Yes, it'll be one element past the end of the entire array when the stack is empty. Mm, we'll actually see how it is used later on. Okay, go ahead. Mm, not you mean, are you asking why we grow backwards? Like, we start at a high location and then as we consume space on the stack pointer moves down? Are you asking about that? No, you could have gone the other way around. You could have moved up in terms of memory location. We could have done that too. So the reason why we grow down, has to do with how we utilize the content of the stack. It has to do with addressing modes, which we are not talking about yet. So the rationale is explained later, possibly in the next lecture, probably next Tuesday. So to pop an item, okay, to remove an item or to retrieve an item, we do exactly the opposite. When I said opposite, it is opposite in two ways. When you look at the ordering of the instruction, SP++ obviously has the opposite of SP++, but you can see how SP minus minus was the first thing to do when we're pushing. SP++ is the second thing that we do when we are popping. And then when we look at how we store something into where the stack pointer points to, this is occurring second, but when we retrieve an item from the stack, it is happening first. So it is reversed in both ways. Okay, it is reversed both in increment, I mean, decrement becomes increment, but also the order of the incrementing and the decrementing of the stack pointer is also now flipped relative to the memory access instruction or the memory access statement. Are we doing okay so far? Yep, go ahead. It's not, yeah. So we cannot really delete anything. In other words, once you pop something from where the stack pointer points to, once you retrieve it, it is still in the array. It is still there. So the stack pointer is more acting like a bookmark to basically say, oh, everything above this point are in use, everything below this point are not in use. So we're simply moving the bookmark around because because we can't really just say, oh, we are deallocating memory location, make that location go away. We cannot do that. Yep, go ahead. When you push again, it is going to reuse locations that possibly was used earlier but are now deallocated. It's deallocated because of this. We move the bookmark back up again. So those locations will now be usable again in case we have another push. Nope, there's no garbage collection here. The stack pointer is nothing more than a bookmark. So imagine you have a binder of paper, right? So you have a bookmark associated with the binder. The bookmark was initially all the way past the last page of your book. And the bookmark is always the sticky, is always on the page that you last used to store something. Is that okay? Can everybody kind of imagine that in your head? You have a bookmark, you got a binder. Whatever page the bookmark is the last page that you wrote something on. Is that okay? So anytime you want to go like, oh, I have another thing that I need to remember. So what you do is you first move the bookmark to a page prior to the one that it was on before. So now you have quote unquote allocated a new page. And on that page, it may not be blank to begin with because this is an old binder that you have been using all semester. So if it has content on the page already, it doesn't matter. Just erase everything on that page and then start with and then overwrite your new content. Is that okay? So let's just say that, oh, okay, this is for me to remember what I need to buy at Albertsons, okay, or supermarket, and I don't need it anymore. So once you have used a page, retrieve the content, and that page is no longer useful to you, what you do is simply to move that bookmark and say, okay, this page is not useful to me anymore. You move the bookmark to the page right after that page. That is how quote unquote you deallocate a page so that it can be used again in the future. But the actual content on that page is still there. You're just moving a bookmark to indicate if I need to retrieve a page, which page am I going to retrieve? Yes. There's no null here. There's because SP will never become a null pointer. The initialization here, the one before this one, it's yes, it's reusing the same page, but it's also overwriting it because the reference is on the left-hand side of the assignment. That is correct, but that's how we quote unquote deallocate. That's how we go like, oh, this page is now available again to be used later on. This is the deallocation of the page. This single statement here is quote unquote deallocating a location so that it can be reused again in the future. Yes, but that's okay. I just need to mark somehow that that location is once again available. That's the whole point of the quote unquote deallocating. That is actually true with dynamic memory allocation as well. Since you guys might have some exposure to dynamic memory allocation, like new and delete or malloc and free, it's the same thing. When you deallocate something, when you free something, or when you delete something that is pointed to by a pointer, nobody is going into the memory chip and use a laser to destroy transistors. That would just not make sense, right? So what is really happening? The block of memory that belong to where the pointer points to is somehow now going into a free pool of memory. In other words, it is just a trick, okay? It's an illusion. That piece of memory is still around, having the same content as before you delete the object, okay? It is just that you have lost references to that location, or it is marked to be reusable again. So that's why dangling pointers is really so bad because in C and C++, you can have multiple pointers called aliasing pointing to the same location. One of those pointers is used for delete, the rest are not changed. So now you have multiple pointers pointing to the very same location that used to be where an object lives, but that object has now been deallocated. So at that point, that same chunk of location can now be reallocated with another new or malloc, which means the content can now be changed. But if the other references to the same location, the aliases are still pointing to the same location, they are now pointing to a location that is no longer what they think it is, and therefore you can that can lead to a lot of really difficult bugs to diagnose. Yes, you first, and then back to Elias. Yep, yep. So you're talking about in a file system, how basically the lowest, the smallest quantum of space on your hard drive is marked used and how it is supposed to be used. So you're correct. Deleting a file simply means the folder or the whatever the folder, however the folder is representing, has lost its reference to the chunk of sectors on the hard drive that is actually storing the information. It is simply marked as, oh, this is supposed to be gone. If you need space again, this is now available. It is going into the recycle bin. but nobody has done anything to erase the content. It is still in the garbage bin with the original content. It is just, excuse me, it's just not in the binder that it used to be on in before. Yep. No. Go ahead. Um, it is, if used properly, it is available again, and you just have to keep track of what is still in use and what is not in use and avoid the situation of aliasing. That is the responsibility of a C++ programmer. Yep. Nope. Nope. All you need is to link your program with a special library so that every delete, every free is going to overwrite those memory locations with zeros. In other words, you would have lost the actual content of where the object used to be. So even if your program is not using the pointers correctly, it would just run into content that is already erased. Yes, go ahead. Not necessarily. It depends on the file system. In certain file systems, the formatting can be done in a very simple way, simply to remove, all the entry points, okay, of all the linked list. But the actual files can still be around for a long time. So yes, yes. So reformatting a drive is not the same thing as wiping a drive. They're completely different. Yep. Yes. So to wipe a drive or to wipe a partition means you're overwriting every sector within that partition with either zeros, which is not secure. You overwrite with truly random data multiple times. Yeah, because there are ways to read between the tracks and actually see what used to be on the track, even if you are to overwrite a sector on the hard drive. So we are talking about actual hard drive, and not a solid state drive in this case. So we are kind of diverging away from the original content here. So I'll answer one more question, and then we'll have to get back on track. Yes, you can still recover data, but depends on the physical geometry of things and how you can position the hard drive head between the tracks. So it does take considerably more effort, to retrieve that tiny little residue of the original signature on the track. So if you wipe the drive while shaking it, it actually helps. Just get your little brother to help. It's like, I'm wiping my hard drive right now. Can you keep shaking it for the next hour or so? Or shoot it. Yep. That is very typical. Yes. Yeah. And on top of that, they just advertise. It's like, come check out what I have on my hard drive. That is so funny. All right. So getting back to this topic here, this is how we initialize the stack pointer, because this is pointing to a location that is not even in the array. Okay, because this is pointing to the next location relative to the last location of the stack. But this is how we initialize the stack pointer to indicate that the stack is empty, because the stack pointer points to the last item that was pushed on the stack. But we haven't pushed anything. The stack is empty. So that means we have to initialize the stack pointer to one location higher than the last item that was actually allocated on the stack. Yep. it would not go back. There's no implicit quote unquote going back mechanism whatsoever with the instruction set that we have on this processor. Everything has to be deliberate. Yep. All right. So I think with all this said, now we can look into calling and returning. So instead of just talking about it, we will go ahead and take a look at some sample programs. Okay. So we'll take a look at call return.c and call return.ttp asm. So one is the C code, one is the assembly code. We just want to do a side-by-side comparison of the two. All right, so starting with the C code, typical thing, okay, void f does not do a single thing. Int main, all it wants to do is to call f once, call f again, and then return 0 as a code exit code. So that's the C code, which is the same as what we have um, in the module. So now we're going to implement the assembly code. So now the assembly code is going to go like, okay, we start with a no op instruction because of a bug in LogicSim. So we have to start with the no op. So now the question is, do you want to implement F and then implement main? Well, most people want to follow the same order, so that's what we'll do. But right now, at the entry point of the code for in assembly, we have to initialize the stack pointer. The stack pointer needs to point to the very last location and one byte past that in the memory space. TTP has a memory space of 256 locations. The last location has an address of 255. So we have to initialize the stack pointer to 256 because it has to be one byte past that end. So now we have to do a LDI, okay, stack pointer with location 256. You can see from the syntax highlighting here that the assembler or the editor in this case does not like it because TTP, text toy processor, actually does not have a stack pointer. We only have the four registers, A, B, C, and D. So in this class, we designate, quote unquote, randomly, register D to be our designated stack pointer. In other words, from here on, when I talk about the stack pointer, in the context of TTP code, I just mean register D. That's all it is. Okay, so that means, oh, okay, there's no SP, fine, we'll just use register D here. Okay, so that's fine. And then somebody's going to complain and say, but we cannot store 256 into an 8-bit register because 256 is 1 followed by 8 zeros, which means it needs 9 digits to represent. So that means this is really saying the same thing as storing a 0 into register D. Okay, this really goes all the way back to um, modulo 256 congruent, kind of discussion. Basically, everything is mod 256. 0 versus 256 mod 256 are the same thing. 0 mod 256 equals to 256 mod 256. So it doesn't really matter whether you specify a 0 or 256, they end up having the same bit pattern in register D. So that's how we initialize the stack pointer. I intentionally do not put any comments into this program so that you can get this code and then add your own comment. Okay. So because I think that would be a useful experience. Okay. It sounds like I'm not doing anything to help you understand this material, but if I want to do more damage, I'll be commenting all my programs fully so that you don't have to do it. If you don't do it, you're not going to think about it and you're not going to absorb the material for most people. Okay, so now we have a JMPI to main because main is the first function that gets called. But it has to be returned here because the halt instruction here. So let me just kind of put main over here. So now the question is, how does main know where to go back to? So the idea is we have to push the return address on the stack. So now we have to push the return address on the stack. What return address? We're going to use L1 here as the return address. So we have to push L1 on the stack. So how do we push L1 on the stack? Can someone remind me what the C code looks like when we push something on the stack? It starts with, okay, minus minus SP or SP minus minus, and then what do we have? So in this case, X is L1 because we want to store the value of L1 on the stack. Okay, first thing first, if the stack pointer is simply register D, how do we implement minus minus SP or pre-decrement SP? Yep, that's it. Decrement D, that's all. Okay. So as I said a little bit earlier, you need to be familiarized with the instruction set at this point because it really is important to do that now. All right, so what do we do about this store something into where register D points to? There's only one instruction that is capable of storing anything into memory or overwriting any location in memory. Nope, ST, that is correct. Okay, so let's start with SP. So SP starts with the first operand, which is in parentheses because we are storing to whatever this register points to. So in this case, everybody goes like, okay, since we're storing to whatever the stack pointer is pointing to, and register D is the stack pointer, so we're just storing indirect to register D, and then we're going to specify L1 here. Except, hmm, syntax highlighting indicates that this is not possible. Why is it not possible? You look up the opcode table. What has to be the second operand of an ST instruction? Nope. The second operand, the second one, the one after the comma. Okay, let's check it out. Okay, so we'll go to the opcode table. So we will look up the opcode table, and then this time we're going to look up the ST instruction. So here's the ST instruction. What has to be the second operand? Another register. That is correct. Okay. So do you think this is a syntactic limitation, or do you think it is an architectural restriction? When I say architectural, it means how the processor is designed. It is architectural. It is not a syntactic thing. Okay. So it's easy for me to say, oh, sure, if you want to specify any expression as the second thing, I can do that. But the architecture does not support it because in order to do a ST indirect to a register, you need two memory accesses. The first one is to read whatever is right after the opcode, just like LDI. And then the second one is to store that to whatever register you wanted to point to. Okay, I cannot do it in a single instruction. And I also need to use a register because the only thing that can specify what you're storing to RAM is coming from a register. That has to do with the multiplexers and the demultiplexers. Okay, so that means this restriction here is architectural. Okay, it is because of how the processor is designed that we cannot store a constant value to where a register is pointing to. We can only store the value of a register to wherever another a register points to. Okay, fine. So that means here we cannot use L1 here. Instead, we have to use another register. Let's pick out register A here. But that also means now we need to initialize register A with label L1 because otherwise register A is uninitialized and who knows what's in register A when we do the store instruction. So this is important because this these sequences of instruction here, starting with the decrement D, this is how we push the return address on the stack so that main, acting as a function, knows where to go back to, which is the address of the halt instruction. Is that okay? Yep, go ahead. It is in the RAM module. Everything that we store into RAM is in that one RAM. We only have one RAM module, which is used to store the opcode, and also the stack is on it too. The stack is okay. So when we load instructions, we are starting at location 0. So when you write programs, your program grows up from location 0 and up. The stack grows in the opposite direction. It starts all the way at the end of that space and it grows going to the lower location. So you would certainly hope that they would not meet one day. Because when they do meet one day, that means your stack is going to overwrite your opcodes and your program is going to die in a horrific way. You first, and then back to the class. Back. Yes. So this part of the program, starting from line 1 all the way to line 10, is not visible to you as a C++ programmer. This part is in the libc, okay, to specify the entry code to main. But this is the reason why main is quote unquote the first function that starts everything, because there's a little bit of a hidden code that is calling main from outside of what you can see in your own program. We can still use register A, B, or C, and in any way we want to. Yeah, yeah, yep. Go ahead. Can we what again? Yes, but the whole point is to illustrate how to call main as a normal function, and that's the intention. And that's what we're going to do. So now the question is, in main, there's nothing to do yet. Okay, so we're going to say, okay, ultimately we're going to call f twice. Okay, fine. So now the question is, how do we return to the caller of main? So at this point, the stack pointer is pointing to the very last thing that we push on the stack. Can someone tell me what we have pushed on the stack? There's only one thing that we have pushed on the stack. What is it? Not the halt instruction, but the address of the halt instruction. So that means, oh, we just have to go back to that location. But we don't want to, kind of use any assumption here. We want to use the stack pointer. In other words, here is what we want to do is to do a pop operation. Can somebody remind me how pop works? And then, okay, that is correct. Okay, so first thing first, okay, so that means I need to pop whatever the stack pointer is pointing to into a register. Okay, that's the only place it can go because the LD instruction, which is the opposite of the store ST instruction, can only retrieve the value of a memory location into a register. That's all it can do. So let's just say that we want to put it into, say, register B. So how do we perform this operation on line 15? The C code is on line 15, but I need to convert it into assembly code. So what do I do on line 16? What instruction should I use? So the first thing is we go to the opcode table and we go like, okay, so how can we do something like what I described? We want to retrieve whatever value that is pointed to by a register and store that value into another register. Which instruction or which mnemonic do you think is going to do that? LD. LD is correct. Okay. Copy and LD are off by one little thing that is super important. CPR is just saying whatever register Y is, copy that to register X. Okay. LD says whatever Y is pointing to, go to that location in RAM, retrieve the content at that location, and then store that content into register X. That little symbol, the asterisk symbol, makes all the difference because CPR does not have any memory access. It is between just two registers. LD, on the other hand, involves reading from memory because register Y is a pointer pointing to the memory location that I need to retrieve. Yes, it copies whatever one register has to another register. So when you look into the register bank, whatever is providing the value is basically having a really tight loop back to the register bank itself in order to update whatever register is the recipient. Do, then you have a duplicate pointer. Then you have an alias of the same location. Okay, so now we say this is LD. I said using register B, so that's how we do this. What about SP plus plus? How do we do that? Just increment what D. That's right. Okay, so we are all good. Now we have the return, the location where we need to return to, or the address that we need to return to in register B. I wish there's a way to copy register B to the program counter, because that's what we're going to do, right? Because the program counter is dictating from which location in RAM should we fetch the next opcode. And if we can control that, then we can control the flow of the program. Does that make does that make sense? Okay. So now the question is, uh, what do we do about that? Okay. This is the one opcode that we really haven't talked about yet because we have not had the need to talk about it yet. So now, so So which row are we talking about in the spreadsheet? We need to update the program counter with the content of just a register. JMP without the I, okay? Because the I sets it has an immediate operand, which means let me tell you where it needs to go, okay? That's what the I is. JMP with X here on row 25 says, hey, just give me a register. What the opcode is going to do is to copy that register to overwrite the program counter. Every time you overwrite the program counter, you are changing where we go to fetch the next opcode, and therefore changing direction of the flow of the program. So now we go back here and we just say JMPB. So this program, even though we have not even got to the point to call function f, is already illustrating how to call. So the calling is done by line 4, if you want to include the comments, line 3 to line 9 is the call. Okay, we have to decrement the stack pointer to allocate a location on the stack. 2, we have to remember where the called function needs to return to. So it starts with line 6, which is putting that return address into register A, and then line 7 in order to store that return address on the stack. Yes, that is a very good question. I'll answer that after I talk about the return instruction, and then we'll go back and answer that particular question. So the return code starts with line 15 if you include the comments, and it ends on line 19. In other words, the function that is done, that has completed and go like, okay, I can go back to the caller now, has to use the stack pointer to retrieve the return address, and then use the return address to overwrite the program counter in order to continue execution at where it is supposed to return. Okay, so to answer your question, TTP is intentionally very simplistic. It is the RISC processors. So most RISC processors still has a call and a return instruction where the things that we do from line 3 to line 9 is done kind of using one single instruction, one opcode, and then all the things from line 15 to line 19 is done by a single return instruction. But if I use call and return as individual instructions, then I cannot illustrate what is going on the stack, and therefore I cannot illustrate the importance of the stack. And that's why in the processor, in the TTP processor, I do not have a call and a return. Yes, go ahead. But it's not the same because main is supposed to be just a function itself. So it is not the job of main itself to halt. It is the caller of main that needs to halt. So yes, I know it seems to be splitting hair, but the less specialized things that we need to specify, which is in this case, oh, main is a special function, it does not return, it just halts. The more special cases that we add to whatever we are designing, the worse it gets. Okay. So there are two things I still need to do. Okay, so we are running out of time a little bit here. The first one is to show you guys how this program runs. Okay, so I think that is actually kind of important. So let me go to the folder where I have River Spider installed. Oh, CISP 310, River Spider, submit call return dot ttp asm. So, all right, so this is all done. And now when we go back to the assembler and go to the analysis tab, this is actually kind of important because it illustrates not only the flow in terms of the line numbers, we can see how, okay, we start with the no op instruction, register D is changed to 0, decrement D. So by the time we store something on the stack pointer is already pointing to location FF. Okay, location FF is the first location that we actually use to store something in a push operation. What are we pushing on that location? By the time we get to line 7, we can see that we are storing 092 F location FF. Okay, so the notation that I use on column C is also intentionally copying and using the dereference operator in C++. So now we know that location FF has a content of 09. And then we continue to go to main, okay, because the entry code has to call main. Main has nothing to do. The first thing it wants to do is to retrieve the return address. So it uses register D, which is FF, and then the LD instruction is retrieving whatever is at location FF, which is our return address, which has a content of 09, and use it to overwrite register B. And then it increments register D to say, oh, I just retrieve the value of that location. We don't need that location anymore. So it increments the stack pointer to indicate that that location, which is FF, is no longer of any use to us. But the most magical part is the JMP B instruction because we can see that instruction is executing more or less sequentially, register location A, location B, location C. But by the time we get to the JMP B instruction, because register B has a value of 09, so that's why we continue execution at location 09 and accomplishing the, the, the return of a function. So even though we didn't quite get to calling F twice, okay, this particular program still illustrates the mechanism of calling and returning. So every time you call a function and return from a function, all of these things are happening. It is just that in C++ programming, all of this is out of sight, okay, and you're not aware of how the stack is utilized. But in assembly language programming, depending on the architecture, you can also just have a call instruction and a return instruction, but I intentionally do not implement those two instructions so that we actually have to understand how this all has to happen in the background. So with that said, let me give you the access code of today's lab. And it is right here. It is called Compiling C Control Structures. This is the one. So now you can see it. And it has 14 points. And then the access code is GCC all in lowercase. Partially because GCC does not work on text architecture. Uh-huh.